Video, I'll talk about one of the most common fragmentations that the amines functional groups undergo. When you have an amine, which means you have a presence of nitrogen, and that applies to amides as well, because amides also has a nitrogen, or a matter of fact, any organic compound has a nitrogen in there, especially an odd number of nitrogens. So if you have, let's say, either 1, 3, 5, and so on number of nitrogen atoms, then your molar mass would be an odd number. So that's one way to tell you if you actually have a nitrogen or not. But then, just because you don't have an odd number, you have an even number, that does not necessarily mean that you don't have a nitrogen. That's because if you have an even number of nitrogen atoms, your molar mass will still be in an even number. So like for example, if you have 0, 2, 4, 6, and so on number of nitrogen atoms in the structure, then your molar mass would be an even number molar mass. So if the molar mass is in an even number, you may have a nitrogen or you may not have a nitrogen. All right. That's just because you have an even number. That does not necessarily mean you have to have a nitrogen, because you can have a zero number of nitrogen. So zero is also an even number. But if you have an odd number of nitrogen, if you have an odd number molar mass, that at least tells you that you got to have a nitrogen in there. So that's kind of pretty certain at that point. So that's something you want to keep in mind. Now, for example, this particular mass spectrum that I got on the right side here has a molar mass of 87. So that actually tells me either I have one nitrogen or three nitrogens or five nitrogens. And you always want to start out with one nitrogen to kind of build up on it. So this amines is actually the one I have drawn on the left side. So this is C5H13 and the nitrogen in there. And I can go ahead and calculate the DOU on that. So DOU on that would have been actually 0 when you do the math on here. So that means there is no double bond, there is no triple bond, no pi bond whatsoever, no ring, and all that. So when I have a lone pair on this nitrogen atom, obviously, that's a non-bonding electron pair, and when it undergoes in the mass spec, I'll lose one of those electrons from that nitrogen atom, and one of the electrons stays there, and that makes the radical cation. So I have an electron lost. So the M over Z for this one would have been 87, and you do see that there, obviously. Now, when you go down and undergo some sort of fragmentations, you typically undergo a fragmentation at the alpha position in case of an amine. That's because you can make a more stable carbocation in that case. So if I do a fragmentation here, where suppose I break it right here. So if I break it right there, I will end up getting, let's change the color here, I'll get carbocation on the left side. So I'll get a carbocation here, and I'll tell you why I would get a carbocation here. So I have a lone pair, don't forget that. Get a carbocation here, and the reason why we can get a carbocation and stabilize that is because of the resonance. So this can resonate in here, and I make a structure that is actually going to have all octets completed now. So remember, in a charge, a resonance structure with all octets completed is going to be very stable. So I'll make that. And the radical I'm going to be making here would be the C2H5 radical. So C2H5 is actually going to be 29. So that means the M over Z for this carbocation that you just made is going to be 87 minus 29. So what's really 87 minus 29? Do the math. That's 58. So 87 minus 29 is going to give you 58. Now, do I have any signal on 58? Well, turns out yes, we do have a signal at 58. That is also happens to be your base peak in this particular case. So that's how you get it. The other possibility could have been here. What if you break it on the left side? Because you still have to make, you have another possibility of making the carbocation from the left side. And if you do go ahead and break it on the left side here, not here, but rather here. So I lose actually 15 here, if I think about it. Then I ended up getting I remember you always do in the homolytic cleavage here where you kind of, this comes down here and this comes down here. So that's why you get a cation on one side. So the right side we get a cation because this, when this bond breaks, you have uh, sorry, hold on, I get the wrong one broken up. I'll break it right here. So one electron goes here, one electron goes here. So when that happens, one of those electrons that you coming up here and you have another electron here, that kind of makes this nitrogen kind of neutral or happy with the bond pair of electrons or the non-bonding electron pair. And you'll still have a positive charge on this one because you have an incompleted octet for this carbon here. But then turns out you would have this carbon here would have a radical. So I'm making a CH3 radical here, and I'm going to be making, I'm just going to go ahead and draw the most stable one here. So if I don't want to draw, let's say, this lone pair here, but rather I'll leave it, the electron here, then this one can come down here, and that makes this nitrogen having a positive charge. So positive charge here. And obviously I can draw the resonance on that if I want. So the resonance on that would have been, I need to put a nitrogen there, hydrogen there, would have a positive charge here. But the first one would be the more stable resonance. So the M over Z for that one would have been 87 minus 15. That is going to be 72. Now, do I have anything on 72? If you come down here, you do have something at 72. Now you can't really explain every single fragments that you see in there because they're a lot complicated. This is like in a basic mass spectroscopy or organic class where we're just going to be focusing on the most common fragmentations of these functional groups.